Hello and welcome to the video lecture on process management. I am Kiran Shinde, Assistant Professor at ICMR MCA Pune. In this video lecture, we will understand the basics of process, the various states of the process, and the basic building block of a process, that is PCB, process control block. So let's start. So basically, in this particular lecture, we will first understand what do you mean by a process. Process is always called as a program in execution. What do you mean by that? When we say that a program is in execution, essentially it actually occupies the various resources such as the CPU time, memory, the required files for that particular program's execution, and the IO devices. So whenever there is a program which is occupying these resources, which is getting allocated with these resources, that moment of time, the program can be called as a process. Processes can be categorized as operating system processes or user processes. Obviously, the OS processes are handled by the system itself that executes system defined code, and the user processes are created and executed by the user. Now, let us try to understand what are the various states of a process. The process can be viewed in five different states: new state, ready state, running, waiting, and terminate. We say that a process is in new state when it is just created. A ready process actually exhibits when the process is in buffer or it is ready with all the desired resources. Right before some time, we discussed about the various resources a process acquires and it is waiting for CPU for execution. Then we say that the process is in ready state. When a process is actually started execution with the CPU, we call it as a running state. When a process is interrupted due to some IO request, then we call that particular process into waiting state. And finally, when the process completes its execution, we say that the process is in terminated state. So with this particular simple diagram, we can understand that how a process actually goes through the new state to terminated state. Let's have a look. So these serial numbers are exhibiting the various states of the process, and in circles, the process states are mentioned. So number one, the process will be created. It will be in the new state. After that, you can see the process has started its execution with, rather it is waiting for the CPU to be executed. So it is in ready state. After it is waiting for the CPU, when it gets the CPU time, then it is actually converted into the running state. At a running state, there can be certain scenarios which can take place, such as suppose when a process is in the running state and it is interrupted due to an IO request, then the process goes into the waiting or block state. Once that particular IO request is resolved, then again the process goes into the ready state waiting for the CPU to be executed. So after this, it will again get CPU time to be executed. Once it gets executed successfully, then it goes back to the terminated state, wherein we can say that the process or the job is over. Now, this is an example of the process states of Unix operating system. You can see that the user running, which is executing in the user mode, kernel running is executing in the kernel mode. So there are two modes which are actually exhibited in this particular process states, a user mode and a kernel mode, which is also called as a system mode. Then we can see that in Unix also there are various states the process goes through, such as a ready state, a sleep in memory state, ready to run, swap state, sleeping state, preempted, created, and zombie state. So as per the operating system, there are various states a process goes through. Now we can just see that a very important concept of process is called as PCB, that is process control block. Whenever a process is created, a PCB for that particular process is created by the system, which keeps each and every information of the process. Each process has its own PCB, and system creates a PCB whenever the process enters into the new state. It creates and destroys PCB when the process enters into the terminated state. So essentially PCB is created temporarily for every process, which keeps the information of the process. Here you can see a simple block structure of PCB, wherein you can see various fields are mentioned, such as process ID, which actually tells about the identification of the process, a number which is given for uniquely identifying that particular process among various processes. The state of the process, just before some time we discussed about a program counter, which will essentially point to the next process or the next task of that particular process to be executed, register information, whatever registers are used for that particular process at that moment of time, the CPU registers, scheduling information, which kind of scheduling algorithm this particular process has become a part of, any kind of memory allocations related to the particular process, then the start of the process, the entire size of that particular process, rather memory requirement of that particular process, and finally status information which is related to input output device. If that particular process is interrupted by any IO request, then that kind of information will also be updated in PCB. So this is nothing but a simple block diagram of process control block. You can also explore yourself for TCB, that is thread control block or task control block. Now, let us talk about a very important concept, that is process scheduling. In order to understand what you mean by process scheduling, there are two terms which we need to first understand. What do you mean by scheduling queue? How the scheduling queue is used in understanding the scheduling algorithms, and what are the schedulers? So the scheduling queues are categorized into three types: a job queue, ready queue, and a waiting queue. And schedulers are categorized into three types: job scheduler or long-term schedulers, CPU scheduler or short-term scheduler, and middle-term schedulers. So basically, what do you mean by scheduling queue? The scheduling queue is nothing but a buffer where processes resides and waiting for the CPU or device or register. So it is nothing but a buffer wherein all the processes will be waiting for the CPU time to be getting executed with the CPU. And these scheduling queues are categorized as job queue, which stores all the processes which are entered into the new state. Ready queue, which actually maintains the queue of all the processes which are into the ready state, which are waiting for the CPU time. And waiting queue or device queue or IO queue holds all the processes which are interrupted due to the IO requests. So here in this particular queue, all the processes are into block state. Now, what are schedulers? Schedulers are nothing but they are actually exhibiting a tool which selects the appropriate processes to be carried out from the bunch of processes. So the main aim of scheduler is to actually select the appropriate process. Means what? What kind of process it has to select. Now very soon we will talk about two types of processes: CPU bound and IO bound process. So scheduler has to decide, or rather scheduler is responsible for selecting a good mix of the process. Okay, and it schedules the allotment of shareable resources. Shareable resources: CPU, IO devices, any files which are required, the buffer, memory buffer, among the multiple number of processes. Schedulers are categorized as job or long-term scheduler, CPU or short-term scheduler, and middle-term scheduler. Now, first of all, let us try to understand what are the two types of processes: CPU bound and IO bound. The processes, those are called as CPU bound processes, those generate the IO requests frequently and so will be more busy with the CPU. So the processes which are requiring more CPU time are called as CPU bound processes. And IO bound process, the processes those generate IO requests very frequently and so will spend less time with CPU. Means the processes which are not requiring the CPU time as much as the CPU bound processes are concerned are called as IO bound process. Very soon I will give you examples also. An efficient long-term scheduler should select a good mix of CPU and IO bound process. Now, what do you mean by this? The main job of the long-term scheduler is to find out the good mix. Means what? It should not only select the CPU bound processes, or it should not only select the IO bound processes. It has to maintain the good mix, balance between the CPU bound and the IO bound processes. Now, there are some examples which are listed in this particular slide: the CPU bound processes, such as search algorithms, video audio content conversion, compression algorithms, video streaming, graphics processing, rendering, for example, games and videos, heavy mathematical computations like matrix multiplication. So these are the examples of CPU bound processes wherein the processes require more amount of CPU time. And IO-bound processes, examples are copying, moving, transferring the downloading files, and collecting applications or OS data snapshots. So these are the examples of IO-bound processes. So essentially, the job of the long-term scheduler is to select the good mix of these processes. The long-term scheduler is slow in speed, of course, because it has to spend much amount of time in this decision making for understanding, rather for analyzing the good mix between the CPU bound and IO bound processes. So a good process mix is required because of all processes are IO bound, the ready queue will be empty and the short-term scheduler will have no work. So every scheduler also should get some work, CPU also should be busy. So all these things the long-term scheduler has to take into consideration while deciding the good mix. So if all the processes are CPU bound, the device queue will be empty and again the system will be unbalanced. That's what I just stated before some time. And this long-term schedulers are implemented between memory and ready queue. What is the role of short-term scheduler? Short-term scheduler selects one process from the ready processes from the ready queue and assign them to CPU for execution. Of course, the work which is allotted to short-term scheduler is quite short, so it is faster in processing as compared to long-term scheduler. It is implemented between ready queue and CPU. And what is the role of middle-term scheduler? This is implemented between CPU and ready queue. It is actually destined or it is actually aimed to take out a running job from CPU and send it back to ready queue. So essentially this middle-term scheduler plays a major role when there is a kind of process which is interrupted due to IO request. So at that time, this particular scheduler shifts that particular process into this scheduler for the time the IO request is getting resolved and then again assign it back to the ready queue. So swapping may be necessary to improve the process mix or because of change in the memory requirements has overcommitted available memory requiring memory to be freed up. So this particular scheduler is used by the system to schedule the processes when a running job is interrupted and swapped out and later swapped in by the medium term scheduler. So these are the three different schedulers. They play a very important role as far as process scheduling is concerned. And now this is the last diagram for this particular lecture wherein you can understand how the different queues are maintained. Now here certain device queues are exhibited, such as you can see there is a queue of magnetic tape, there is a queue of disk, there is a queue of unit, terminal unit, okay? And these are nothing but the various processes which are in line with those queues or those device queues. So essentially it is exhibiting a linked list like structure, okay, to understand how the queues are maintained across every device. So here we are going to stop. Hope you understood today's topic, and next video lecture we are going to learn what are the various scheduling algorithms. Stay tuned for my next lecture.